Section 7.5, Electron Affinities. The first ionization energy of an atom is a measure of the energy change associated with the removing of an electron from the atom to form a positively charged ion. For example, the first ionization energy of chlorine gas is 1251 kilojoules per mole. It's the energy change associated with the process of changing chlorine into chlorine plus an electron. The positive value of the ionization energy means that the energy must be put into the atom to remove the electron. In addition, most atoms can gain electrons to form negatively charged ions. The energy change that occurs when an electron is added to a gaseous atom is called the electron affinity, because it measures the attraction or affinity of the atom for the added electrons. For most atoms, energy is released when an electron is added. For example, the addition of an electron to a chlorine atom is accompanied by an energy change of negative 349 kilojoules per mole, the negative side indicating that the energy is released during the process. We therefore say the electron affinity of chlorine is negative 349 kilojoules per mole. It's important to understand the difference between ionization energy and electron affinity. Ionization energy measures the ease with which an atom loses an electron, whereas electron affinity measures the ease with which an atom gains an electron. The greater the attraction between a given atom and an added electron, the more negative the atom's electron affinity will be. For some elements, such as the noble gases, the electron affinity has a positive value, meaning the anion is higher in energy and there are separated atom and electron. The first fact that electron affinity is a positive number means that the electron will not attach itself to an argon atom. The argon ion is unstable and does not form. Figure 714 shows the electron affinities for the S and P block elements in the first 5 rows of the periodic table. Notice that the trends in electron affinity as we passed through the periodic table are not as evident as they were for first ionization energy. The halogens, which are the 1 electron shy of filled p subshell, have the most electronegative electron affinities. By gaining an electron, the halogen atom forms a stable negative ion that has a noble gas configuration. The addition of an electron to a noble gas, however, requires that the electron reside in a higher energy shell that is empty in a neutral atom. Because occupying a higher energy subshell is energetically very unfavorable, the electron affinity is highly positive. The electron affinities of beryllium and magnesium are positive for the same reason. The added electron would reside in a previously empty p subshell that's higher in energy. The electron affinities of the group 5 elements, nitrogen, phosphorus, arsenic, and antimony, are also interesting. Because these elements have half-filled p subshells, the addition of electron must be put into an orbital that's already occupied, resulting in a larger electron repulsions. Consequently, these elements have electron affinities that are either positive or less negative than their neighbors to the left. Recall that we saw a discontinuity in the regular periodic trends for first ionization energy in section 7.4 for the same reason. Electron affinities do not change greatly as we move down the group. For example, consider the electron affinities of the halogens. For fluorine, the added electron goes into the 2p orbital. For chlorine, the 3 orbital. The bromine, the 4p orbital, and so forth. As we proceed from fluorine to iodine, therefore, the average distance between the added electron and the nucleus steadily increases, causing electron-nucleus attraction to decrease. However, the orbital that holds the outermost electron is increasingly spread out, so that as we proceed from fluorine to iodine, the electron-electron repulsions are also reduced. As a result, the reduction of the electron-nuclear attraction is counterbalanced by the reduction in electron-electron repulsions.